Welcome back, folks. I decided to stay on the beach for this one. And, man, that water looks good. I'm really in a basement. There's no water. There's no beach. Let's do some nodal analysis. Okay. Still working with dependent supplies. I promised you a dependent supply that was a voltage supply this time, just to mix it up a little bit. And we can see that right here in the middle, and it is a voltage supply because it's got the plus and minus on the inside, and it's controlled by a current. So it's a current controlled voltage supply, and we treat it as such when we do our nodal analysis. Okay, first things first, how many nodes? So take a look at it. I think this is a nice obvious one. I think this is a nice obvious one. I think sometimes people get lost up here, but look at all of that. I don't have to cross a component. That's all one node. Okay, so I can label it anywhere. We'll label it right there. Is that still on the screen? Yep. Okay. So passive components get an arbitrary current direction, like so. Whee! Getting tired. I'm getting a little slap happy. Does it show? Good times. Okay. How many KVLs? How many KCLs? We still play this game. How many voltage supplies do we see? Well, I gave away one, right? The dependent supply is a voltage supply. So I still write a KVL for that. And then I also have this voltage supply. So I'm gonna write 2 KVLs, and I'm gonna write 1 KCL. And that's going to cover my 3 unknowns. I'm going to have 3 equations for my 3 unknowns. Furthermore, check out that voltage supply, huh? What's going on there? It's connecting 2 non-reference nodes. And because it's connecting 2 non-reference nodes, it is in fact a supernode. Okay, so we bound that region and declare it to be a supernode. Okay, let's write some KVLs. Let's do it. Which one you want to do first? I wish you were here to tell me. Since you're not here to tell me, I'm going to pick. I'm going to do the super one first, since that's kind of part of the interesting thing about this problem is the super KVL. So I'm looking at this supply. VB is on the positive side. VA is on the negative side, and that is equal to whatever the supply is labeled. So in this case, it's going to be 4IX. Okay. Now, it's not quite ready for prime time because I have this control variable. I got to get rid of that, and I get rid of that by looking for that variable. There it is, and how it's labeled in the schematic, and I write an expression for it. So IX is equal to, ooh, I didn't follow, oh, look what I did. That's going up, I labeled down. I think we'll be okay. When I'm writing IX, I'm using the white label there, okay? So this is going to be VB minus VC over 12. Okay, so I've got to substitute that in there. I'm going to rearrange VA and VB just out of habit. And I'm going to have 4 times 12. I'll write it out. Never skip a step if I can. Okay, so we plug that in like that. That's going to be 1/3, right? 4 divided by 12 is 1/3. So I can distribute that. So I'm going to get negative VA plus VB equals 1/3 VB minus 1/3 VC. Now I just got to get those over to the other side of the equation. So negative VA, and then I'm going to subtract 1/3, right? So I have 1 VB, and I'm subtracting 1/3 VB, so I'm going to end up with positive 2/3 VB. Okay, adding 1/3 VC to both sides, I get 1/3 VC, and it drops off, and that's equal to 0. Nothing outrageous, hopefully, for you, but there's your equation. Bunch of constants, only the unknown node voltages, we're good to go. Okay, is that the only crazy one? No, of course not. We got to write the KCL for the supernode. All right. And let's do it in white. Come on. KCL for the supernode. And it looks like I've got 1, 2, 3, 4 currents to think about. So let's start up here, and we've got VC minus VA over 8. I'll come down here. We've got minus VA over 24. Moving back up to this one. It's going in, so it's minus, plus. It's going in, so it's plus. VC minus VB over 12. And this one is leaving, so it's minus VB over 6. Right? It's VB minus 0 because the other side's ground there. And that's equal to 0. Oh, that was all behind my head. There it is. Hopefully you're following along. The image is posted for you. So you've always got that option. Okay. Let's see here. Doing some algebra. So we got negative 1/8 and negative 24. So what is this? This is going to be 3/24, negative 4. So it's going to be negative 1/6 VA. Where are my VBs? Over here and here. So I got negative 1/12 VB and negative 1/6 VB, which is going to be negative 3/12, also known as negative 1/4 VB. All right, and we got VC 1/8 and 1/12. 24 will work. So we've got 3/24 and 2/24, so it's going to be 5/24, and it's plus. I don't trust myself when I do like simple arithmetic. Now I'm trying to do fractions in my head while I'm ready for a nap. We'll see how this goes. And that's equal to 0. Okay. There's our second one. Last one, super easy. Super easy. It's the KVL. Oh, you didn't see that. There it is. Sorry, it was behind my noggin. Last one is the KVL for C. What's connected to the positive side? VC. What's connected to the negative side? Ground. And that's equal to whatever the supply is. Okay. Nice and simple for that one. Okay. VC is connected to the positive side. Ground is connected to the negative side. And that's equal to 15 volts. Yep, 15. Okay, that 0 drops out. And we get VC equals 15 volts. Yes, I know you probably can look at that and go, well, it's connected there. Of course VC is equal to 15 volts. There's a method. Follow the method. Don't screw up the signs. Okay? So 15 volts for that one. All right, there are 3 equations. Now we just got to solve it to find the node voltages. Okay, so negative 1, 2/3, 1/3, negative 1/6, negative 1/4, 5/24, and 0, 0, 1. Here we go. Okay, right hand sides, we got to make sure I do it in the same order here, so that's 0, 0, and 15. Doing that little bit of linear algebra is going to give us our vector of unknowns, VA, VB, VC. Okay, and hopefully we got some values for that. So let's go ahead and do that together, all together, but apart. Negative 1, 2/3, 1/3, 0. Negative 1/6, negative 1/4, 5 divided by 24, 0, 0, 0, 1, and 15. The noises help. They really do. 9.23. And of course I'm rounding just a little bit. 6.35. These are both in volts, and then of course that's 15 volts. If it's not, something's really, really wrong. Okay. So there are node voltages. What were we finding in the first place? I don't know if I even mentioned it at the top of the video, but let's go look at the problem and see what it is. Okay, so I have this I out labeled over here. Okay, so let's find that. Find I out. So it's not the control variable, and that doesn't really matter too much because it's just another value, but it means we got to write another equation. Okay, so if I'm finding that current, and it's the current through the voltage supply, so we have that problem where we can't find the current directly, so we're going to have to think about our fundamental rules. Can't find a current with KVL, okay, because everything's a voltage in KVLs. Ohm's law, well, we don't know the resistance, so we really can't do anything about that. So that leaves us with KCL. So I have to write a KCL that involves that current. I can either write it up here for C. I could write it down here for the ground node. There's absolutely nothing wrong. And if you do both, it should end up being consistent. Again, where I would usually, I need a coin. I would usually ask you, I would say, which one do you want to do, the node C or ground? They're going to get you the same answer. Hold on, let me find a coin. Okay, it's a 2017 Ellis Island commemorative quarter. So heads we do C. Here we go. See, it's right there. Can I get that to focus? It's got a cute little picture on the back. Heads we do C, tails we do ground. Doesn't matter. Okay. Heads, we're doing C. Okay. How fun is that? I'm doing what I can, okay? All right, so we got three currents. I out is one of them, and it's going in, and then the other two are leaving. So I'm going to pull up my notes. Oh, there's my notes. Ah! Didn't realize they were on the same monitor. There we go. Okay. And let's write this out. Okay, so we have three currents. I'm going to start with the one on the left for R1. It's leaving. I'm writing a KCL for node C. Usually we would have avoided that because it has voltage supplies connected to it, but we need it now. Okay, so VC minus VA over 8 minus VC minus VB over 12, and I out is going in, so it's going to be plus I out, and that's equal to 0. Okay, so we added an equation because we added the unknown of I out, and that's going to be okay. We just got to plug it in. Okay, so let's plug it in. What do we got? 15 minus, let me grab my numbers here. Oh, I don't have my numbers here. Let's scroll down a little bit. 15 minus 9.23 over 8. So there's a skosh of arithmetic to do here. Minus 6.35 over 12. And that's going to, why isn't this one minus? It's leaving. I'm going to take a nap after this. We're taking a break before we start op amps. I'm taking a break. I don't know about you. You keep pressing play. Hit that like button, subscribe, whatever you want to do. Whatever the YouTubers do nowadays. And we can move that I out over, and it's going to be negative. But if I multiply left and right, everything becomes positive. Okay, so we just have a little bit of arithmetic to do to figure out what I out is. Okay. 15 minus 9.23 divided by 8 gives me like 0.72-ish. Okay, we got 15 minus 6.35 divided by 12. And we're going to add that to our previous result. And we get 1.44. And that's, of course, in amps. All right. Okay, so sometimes we have to use our fundamental laws to go find that the value that we're interested in. I think we did one of those when we didn't have dependent supplies. In this case, we had to do it again because we had a dependent supply. This one was a current-controlled voltage supply, and it was a voltage supply that was connected between two non-reference nodes, so we've had to form a supernode. But we take the same approach. Other than that substitution, everything else is the same when we add dependent supplies to a problem we're using nodal analysis on. Okay? So you certainly have some of these in homework. We're going to have some on the exam. We're going to have some in life. It's just how we build things. Okay? So coming up next, another component, a new component that we haven't touched, but we can use nodal analysis. And I like using nodal analysis on this type of problem. So get excited. Stay tuned. Good luck.